nomenclature bonus. I did the nomenclature bonus because you might have, let's say, not done as well on the first exam, so you still have a chance to do well in the class if you can do well on the second and the third exam and the final. And so I bumped it up because the average on the first exam was less than 50, which is pretty low. And so this will give a chance rather than, if you fail the first exam, you might think that it's going to be fatal for the course, but which it could be. I mean, it depends on how the second and third exam, but to help you out, then I added that. So I'm not sure if you checked on Canvas, but the additional 8 points helps a lot. However, if you don't do the homework, that hurts a lot, because the homework's worth 30 points. Mm-hmm.
So how many points was the extra?
You mean for the nomenclature?
Yeah, you said the one you added yesterday.
Oh, how many extra credit points?
How many was supposed to be added?
It wasn't that much. I think that one is probably going to be, it's either 3 points or 6 points. Each chemical reaction problem, I think, was worth 3 points. And so 3 or 6. I'll have to look at how the results come out.
The green you added yesterday that was the one we did the note card quiz, right?
I'm sorry?
The green you added yesterday for the exam one bonus, was that the note card quiz we took?
Yeah, the note card quiz.
And how many points was that added?
That was worth 8 points, so that was like 8 points worth of extra credit. It was 7.99 points worth of extra credit. And since there weren't that many points in there, it bumped up. It could have bumped you up almost maybe a grade or something. It'll make less impact, with time and as the points accumulate, but initially it would help for the first test. Combining that. So, what was that? And then on yesterday's test, one of the problems had an error in the answers. That was the problem with the combustion of methane with air. I don't know if you caught that, but did anybody catch that? No? Okay. I'll talk more about it later. All right, so today what we're going to do is, if there are no questions, we're going to just continue with Chapter 7. So let me grab my... All right, so we're going to talk about Chapter 7. Chapter 7 deals with energy, or thermodynamics. And we split it up into 2 chapters. So one chapter of thermodynamics comes in Chem 1A. The second chapter of thermodynamics comes in Chem 1B. Well, Chem 1A and Chem 1B. Thermodynamics is one of those topics. It's like all that, oxidizing agent, reducer, oxidizer, oxidation, reduction. All those terms get mixed up. In thermodynamics, there are a lot of terms and a lot of symbols, and it's easy to get mixed up. So thermodynamics is known as a very challenging topic. There's debates about what the hardest class is. Is it thermodynamics or organic chemistry? So people think about this. So it's tough. So the easiest way to get a grasp of it is to just make sure you drill down the terms. It's like you don't want to get confused anymore about what an oxidizer is or what a reducer is. Because if you're still shaky on those terms, then doing anything with those terms is going to run the risk of getting the wrong answer. And so the same thing happens with thermodynamics. There are a lot of restrictions and terms that we need to make sure that we drill down so that we understand these completely so we don't get mixed up. And so when we're thinking about energy, what are the two most common units for energy that we use?
Joules.
Joules. Yeah. Joules is the most common in chemistry. The joules is also defined as what? A kilogram meter squared per second squared. Basically, when we look at the units, kilogram meter squared per second squared, the way we can visualize this is it's like raising a 1 kilogram mass up to a height of 1 meter against the force of gravity. Gravity is in meters per second squared. And so it's taking a kilogram, lifting it up a meter against gravity. And it would take 1 joule of energy to lift 1 kilogram up to a height of 1 meter. And so this is a mechanical definition of energy. And so that's it. The other unit of energy would be the calorie. Calorie is defined differently. What is a calorie, or how is a calorie defined? One calorie is the amount of energy required to it's the amount of energy required to warm up. You know, the definition of the calorie is the amount of energy required to warm up a gram of water by degree C. And so this comes from essentially this. Calories, the energy required to warm a gram of water per degree C. That's what we call the specific heat of water. And so specific heat of water is 1 calorie. How many joules would it take to warm up a gram of water by degree C? Do you know the conversion factor between joules and calorie? There are 4.184 joules per calorie. And so joules is a little less energy, so it takes less energy to raise that kilogram. It would take about 4 times that energy to heat up a gram of water at degree C. So it's not that much. We also have another one. And this other one is the calorie, but it's spelled with a capital C. And so this is the food or nutrition calorie. The food or nutrition calorie is 1,000 chemical calories. So 1 food calorie is equivalent to 1 kilocalorie. And so if you have, let's say, 100 calories, food calories, that's actually 100,000 chemical calories. With 100,000 chemical calories, then you can do things like heat up water, etc. So, when we're thinking about energy, oftentimes we'll think in terms of total energy. Total energy, we give a name to this, and the name that we give is internal energy. So the internal energy is the total energy, and we give a symbol to that. The symbol for internal energy is U. That's the total energy. And if we want the total energy of anything, let's say I want the total energy of this. Let's say I have a beaker, and this beaker contains 50.0 grams of H2O liquid at 25 degrees C. And so I have a beaker of water. And what I want to know is, what is the total energy of this? Can you tell me what is the total energy of a beaker of water at 25 degrees C? how many calories do I have? How many joules? Well, a lot of people say water is calorie-less. But that's, you know, if you're trying to eat it. But we're not trying to eat it here. We just want to know how much energy, total energy. Is it zero energy? Because, you know, if you try to eat it, is anything, are you going to get energy from that? Or is anything going to happen? Well, you get hydrated, that's important. And so we got to think, you know, how can I figure out what is the total energy of that 50.0 grams of water? What would you say? Do you think it's zero? It's not. It's not zero. Well, if it's not zero, then what is it? Well, we know that the total energy is equal to what? I'm sorry? Yeah, total energy is internal energy, which is U, which is equal to when we think about energy, normally we think of them two types of energy. Do you know what the two types of energy are? That we often think of it? Potential and kinetic energy. And so when we think about the total energy, we think about the potential energy, which I don't have a symbol for. I'm just going to call it PE for potential energy. And kinetic energy. Kinetic energy I do have a symbol for. What is the symbol for kinetic energy? Try to get some energy here in this bar.
The U, lowercase u.
That's the speed. Speed is related to energy, but it is not energy. It's just the velocity. The energy is equal to 1/2 times the mass times the velocity. That's one of Newton's equations. Velocity squared. People use different symbols for kinetic energy. We're going to use this, E sub K. Kinetic energy is related to what? Motion, movement. Is that water moving? In a way, it's not moving. It's just sitting in a beaker. But is it moving? Yes, it is moving. Even though it's sitting in a beaker and it doesn't appear to be moving, it's moving. What's moving in the water? The molecules are moving. The molecules are going to have what types of motion? Can the water molecules translate? Yes. Liquids. Can the water molecules rotate? Can they vibrate? And so when we're looking at the kinetic energy, there's energy, this can be broken up into three. Translation plus the energy of rotation plus the energy of vibration. Are there any other kinds of motion? Or are there only three? Or are there infinite number of motions? How many different kinds of motions are there? Well, that's it. Just those three, fortunately. And so I just need the equations for translational. Well, one of the equations for translational was given in the last chapter. A translational kinetic energy is just equal to 1/2 mu squared. Is it? Then I need some equations for rotational and vibrational. But you know what? We're not going to get into that because we know that kinetic energy is directly proportional to what? Kinetic energy and what are directly proportional?
Temperature.
Temperature. And so here's the kinetic energy here. The temperature is a measure of the average kinetic energy. And so, you know, going back to the equations, we can figure out what the average kinetic energy is by using that, you know, T, what is it? 3RT square root, something, no, not square root, 3RT. So anyway, it's the temperature. So the kinetic energy is related to the temperature. You know, in fact, the kinetic energy is going to be proportional to the temperature. If the temperature is 25, then it's going to have some kinetic energy. At what point will the kinetic energy go to zero? Will it go to zero? Can we get the kinetic energy to go to zero? How can we get the kinetic energy to go to zero?
Dropping the temperature.
Dropping the temperature. Dropping the temperature is going to lower it. Will the kinetic energy go to zero? The kinetic energy of water. What happens at minus 273.15 degrees C, or 0 Kelvin?
The absolute zero.
What happens at absolute zero? Do the water molecules translate? No, so translational kinetic energy is zero. Do the water molecules rotate? Rotational kinetic energy is zero. Do the water molecules vibrate? No. And so at 0 Kelvin, the kinetic energy will be zero. Because they aren't moving. And kinetic energy is the energy of motion. The only thing that will be moving at 0 Kelvin are what? Do you know what doesn't stop moving at 0 Kelvin?
Electrons.
Electrons. Electrons don't stop moving. And therefore, this is called the 0 point energy. We aren't going to stop the electrons, but the kinetic energy could go to zero. And so we have kinetic energy here. The kinetic energy is not zero. The kinetic energy is much higher, because we're at 298 Kelvin. 298 Kelvin, there's lots of motion of the molecules. And so we can figure out how much kinetic energy we have just by doing a simple calculation with the temperature. If the temperature is zero, kinetic energy is zero. And we can just increase it. This has to be absolute because we aren't going to have negative energy here. Okay, let's do the same thing with potential energy. So we definitely have kinetic energy here. Do we have any potential energy here? And so how do I visualize, or how do I think about potential energy? Kinetic energy is easy because this is motion, energy of motion. So does this have zero potential energy? So potential energy is a bit different. In this case, I mean, we think in terms of what can water do. One thing water can do is it can vaporize. And so if I have water vapor here, you know, the vapor pressure of water at 25 degrees C, I'm going to have some water vapor molecules here. Are these water molecule vapors in the gaseous state going to be the same as the water molecules here in the liquid state in terms of potential energy? And the answer is no. Which one will be higher potential energy? The water molecules in the gaseous state or the water molecules in the liquid state? Now, what that boils down to is this. How can we get the liquid to go to gas? I mean, why do we see any vapor here? Why doesn't, you know, this is at 25 degrees C. At 25 degrees C, water is not boiling. However, it is evaporating a little bit, and that evaporation is caused by what? Well, at 25 degrees C, are all water molecules moving at the same speed? They aren't. The kinetic energy is a measure of the, you know, well, actually temperature. The temperature is a measure of the average kinetic energy. And so on average, yes, they're moving at the same speed. We call that speed the URMS speed. But individually, they don't necessarily move at the same speed. In fact, there's going to be some kind of distribution. What's that distribution called? The Maxwell-Boltzmann distribution. In the Maxwell-Boltzmann distribution, there's going to be a small population of high-energy molecules. Why do we need high-energy water molecules to vaporize? Why can't low-energy water molecules vaporize? Why do we need that high energy? The reason we need it is that water molecules are really sticky. So if you want some to break free, you're going to have to knock it off with some energy, right? And so what we see is this. When we think about potential energy, there's potential energy here because the water molecules are stuck together. In order to break them apart, we have to break what's causing them to be sticky in the first place. And what's causing them to be sticky in the first place are hydrogen bonds. Hydrogen bonds are intermolecular forces that are quite strong. And then so we have to break apart the water molecules. So when you break something, does it cost energy or does it consume energy? Oh, well, cost is and consumes the same. Or does it release energy? So if we were to break apart the water molecules, do you have to add energy or do you have to remove energy to break apart? You have to add energy. We have to add energy to break apart the hydrogen bonds. Well, that's potential energy. And so this is what we're talking about in terms of potential energy. And so as these water molecules get stuck back here, we're forming hydrogen bonds. And then the first law of thermodynamics says that energy is neither created nor destroyed. And so if it costs a certain amount of energy to break, then we're going to release a certain amount of energy when it's formed. And so if it costs us 25 kilojoules per mole to break, then when they form, they're going to release 25 kilojoules per mole. And so in order to figure out what the potential energy is, we try to break it apart. So if we stay with H2O liquid, the first thing that has potential energy are the hydrogen bonds and the dispersion forces holding the water molecules together. In other words, the intermolecular forces of attraction that hold them together. The other place where there's energy stored are in the bonds. So once we break them and then we have an isolated water molecule, the next thing is we can break the hydrogens off the oxygen. In other words, we can break the covalent bonds holding the hydrogens and oxygens together. Does that cost energy to break the bonds? Yes, it does. It costs a lot of energy, a lot more energy than break hydrogen bonds. To break this covalent bond costs over 400 kilojoules per mole. And so when we break the bonds, that is going to cost energy and it's going to break apart the atoms. However, when the atoms come together to form bonds, the first law of thermodynamics says energy is neither created nor destroyed. So if it costs us 400 kilojoules to break, when we form it, it's going to release 400 kilojoules. And so we say that there's potential energy in the bonds. So there's potential energy in the hydrogen bonding interactions that hold the water molecules together. There's potential energy in the covalent bonds that hold the water molecules together. In this case, there'd be about 800 kilojoules, over 800 kilojoules per mole worth of energy. Okay, so once we break the atoms apart, then we have hydrogen atoms and oxygen atoms. Is there potential energy in hydrogen atoms and oxygen atoms? There is. What's that potential energy? That potential energy is the energy holding the electrons to the nucleus. That's Coulombic. That's a Coulombic attraction. Coulomb's law. And so, in order to remove the electrons from the atom, does it cost energy or does that release energy? So, in order to pull an electron away from the nucleus, and what's holding the electron to the nucleus is a positive nucleus with a negative electron. Do you think it's going to cost you energy to pull the electron away from the nucleus? Yes. And so there's potential energy in the electrons being held to the nucleus. Okay, so we can pluck off all the electrons off an atom, and that's going to cost us more and more energy. And so we say there's potential energy there. And now we're left with electrons over there and a nucleus. Is there any energy inside the nucleus? Potential energy inside the nucleus? There is, because the protons and the neutrons are held together. And these protons and neutrons, what we can do is we can break apart the nucleus into individual protons and individual neutrons. Breaking apart the nucleus, do you think that's going to cost energy or release? That's going to cost energy. So to break apart the nucleus, there's potential energy stored there. We're going to break the nucleus up into protons and neutrons, or nucleons. Okay, finally we must be done, right? Is there any more potential energy left? You know, I broke apart the nucleus, I broke apart the atoms, I broke apart the water molecules. Is there anything else left to break apart?
Like quarks.
Yeah, unfortunately there's more, because the protons and neutrons, that's about the limit for chemists, but physicists will know that protons can be broken up into quarks. Quarks are even smaller pieces that the protons are made up of. And so we can break up the protons and neutrons. Does that cost energy? Yes, that costs energy, so there's potential energy stored in the protons and the neutrons. Okay, now we finally have the quarks. Are we done? That's got to be it. We got to stop there. Is that correct? Or can individual quarks be broken up into smaller pieces? Is that possible, or is that impossible? Or do we know? Well, I don't know, but do you know? Can the quarks be broken up into even smaller pieces? Because if so, then there's potential energy there as well, correct? Okay. So, well, let's stop there. We're going to go to quarks. Actually, for chemists, we probably don't want to. What I want to know is this. I know the absolute zero of kinetic energy. The absolute zero of kinetic energy, nothing's moving. That's got to be 0 Kelvin. What's the absolute zero potential energy? Once I've broken everything apart, there's nothing left to break apart, and therefore there's no more potential energy stored in there. And so is the quarks, would that be the absolute zero? And then I'll call that zero energy. Once I get to the quarks, it's zero. And then I take the quarks and build a proton that's going to release energy, because one way to break apart the proton costs energy, the opposite must release energy. So when I form bonds, you release energy, because when you form bonds, things become more stable. When you break bonds, it costs you energy, because when you break bonds, they become less stable. So, in other words, the kinetic energy, this is easy to determine. You can just use the temperature for that. However, the potential energy is not easy to determine. The kinetic energy can be calculated accurately. You know, if you have the temperature, you can calculate the average kinetic energy pretty accurately. However, the potential energy cannot be calculated accurately. There are just too many things in this calculation. And so the potential energy is difficult to calculate. And if you try to calculate the potential energy, the type of error inherent in those calculations makes the number not useful for any kind of prediction. Calculations contain significant error. And so although I want to know what we call the absolute internal energy, I want to know what the absolute internal energy is, I have problems. Because I can determine the absolute kinetic energy, but I cannot determine with any accuracy what the absolute potential energy is. You know, are quarks really the final building block of matter? And then with all those calculations are difficult. And so we don't calculate it. Absolute internal energies are not determined. They can be estimated roughly, but they are really, I should say, not determined. They can be roughly estimated, but those rough estimates aren't going to be useful for us because the errors are too big. So I'm thinking about potential energy. Where should I put water? Is water at the absolute zero potential energy? No, it's up here somewhere. And so this is called an energy level diagram. And in this energy level diagram, there are no numbers here on the internal energy. And I'll pull out internal, we just know it increases. So the higher up we go, the greater the internal energy, the absolute internal energy. And so over here, I'm going to have 50.0 grams of H2O liquid at 25 degrees C. Things can have lower potential energy and things can have higher potential energy. In fact, I could take this And, well, actually, potential. Let's go with internal. Things can have lower internal energy and higher internal energy. So, for example, let's say I warm this water up. I go from 50.0 grams of water, liquid at 25 degrees C, and warm it up to 50.0 grams of liquid water at 100 degrees C. So we heat it up to 100. Now, when we think about this here, let's say we start off here at 25 degrees C. This is my U initial. And I end up here, this is my U final there. And those are going to change in my internal energy. And that will be called delta U. So U initial here, this is just equal to the potential energy initial plus the kinetic energy initial. And then U final here is equal to the potential energy final plus the kinetic energy final. And delta U here is going to equal the change in potential energy plus the change in kinetic energy. All right, so let's take a look at the change in potential energy here first. Was there a change in potential energy? Let's see, I start off with H2O liquid, I end up with H2O liquid. Did I break anything apart? No. And so the change in potential energy actually turns out to be 0. You know, I started with liquid water, I end up with liquid water. There was no change in potential energy. Was there a change in kinetic energy? Yes. There is a change in kinetic energy. And that change I can measure quite accurately, actually. The change in kinetic energy here is going to equal, well, there are different ways I could do it. I could use the equations from kinetic molecular theory, or I can do it this way. I know that the energy is going to be related to the amount, or the mass, of water. You know, the more water, the more energy it takes to do this change. The less water, the less energy. And so it's going to depend on the mass of water, which is 50.0 grams. And then we're going to have C, which we call the specific heat. The specific heat of water is 1 calorie, or 4.184 joules per gram degrees C. And so this gives us an easy way to calculate the change in kinetic energy. The change in kinetic energy is going to be just directly related to the change in temperature. But temperature is not the units of energy. And so we have to convert it to units of energy. We're going to convert it using the specific heat. We use the specific heat, we got to get rid of the degrees C and the grams. And we have it. So whenever we see a change in temperature, it's going to be related to a change in kinetic energy. Whenever we see a change in temperature, we like to measure it. And measuring changes in temperature, that's called calorimetry. Calorimetry is going to relate temperature changes to energy changes. That's when we have something called a system that is an object. In this case, the object would be 50 grams of water. And the 50 grams of water is just warming up. We have something called the heat capacity. The specific heat relates the change in temperature to energy. But in general, we can do that with different units. So the specific heat is per gram. Typical units are joules per gram degrees C. We like to work with joules in chemistry rather than calories. Then we have the molar heat capacity. So rather than working per gram, we do it per mole. So this would be joules per mole degree C. It's a molar heat capacity. Or we have the heat capacity of an object. For example, a brick. A brick you don't necessarily want to weigh. You know, how many grams does that brick weigh? You know, let's say you built a wall and you used 1,000 bricks. Do you want to know how many grams of bricks that is? Not really. You probably just want to do it per brick. Or like a house. You know, how much heat does it take to warm up the house? How much heat does it take to warm up the brick? Are they going to be the same heat capacities? No, they're going to have different heat capacities. But they'll have the same kind of units. It's going to be joules per object per degree C. Now, if we're dealing with bricks, then we probably say joules per brick per degree C. So this is how many joules it takes to warm up one brick by 1 degree C. But if we're dealing with a house, you know, it's probably just only going to be one house, right? You probably aren't going to be looking at 1,000 houses. And so if we did it here, it's probably joules per object per degree C. But if we always only work with one object, then we'll just say joules per degree C because we only work with one house, not multiple houses. And so over here we'd say joules per brick per degree C, because we could have multiple bricks. But here, in terms of houses, it's just going to be joules per degree C. Since we're working with liquid water, we can have any number of grams of water, so it makes sense to do it joules per gram degree C, because what if I had 52 grams? So now I have a way of determining what the internal energy change is, and this is an accurate calculation. So the difference is, in absolute internal energies can't be determined accurately. However, changes in internal energy can be calculated accurately. And so delta U can be calculated or measured accurately. And so when we do a delta U, we'll never do this kind of calculation. Delta U is equal to U final minus U initial. We'll never calculate it like that. And this is going to equal the change in potential energy plus the change in kinetic energy. So let's go ahead and calculate the change in internal energy here. I don't know what the starting internal energy is. And so there are no numbers on the y scale. And I don't know what the final internal energy is because I have to figure out the potential energy. And that potential energy calculation is going to be tough. So I'm going to ignore the absolute and the final internal energies. I mean the absolute initial and absolute final internal energy. And just go on to calculate delta U. So calculating delta U, the mass is 50.0 grams. Do you know the specific heat of water? The specific heat of water is easy to remember because it's just the definition of the calorie. And the calorie is equivalent to 4.184 joules. So we'll just go with 4.184 joules per gram degree C. So a lot of people have this memorized. And what is my delta T? The delta T is T final, 100 degrees C, minus T initial, 25 degrees C. So my delta T is plus 75 degrees C. So let's go ahead and calculate what the change in internal energy is. 50 times 4.184 times 75. Oh, how did I get a different number this morning? What did I do in calories? I get an internal energy change of 15,690 joules, or 15.6 kilojoules of energy. So the the total energy changed by about 16 kilojoules here. In other words, in order to heat 50 grams of water from 25 degrees C up to 100 degrees C, that's going to cost me 15.6 kilojoules. And that was the total energy change. And it's all kinetic energy. Where's this energy going to come from? Because first law of thermodynamics says that energy is conserved. Energy is neither created nor destroyed. And so where does this 15.6 kilojoules of energy come from? To warm up my water from 25 degrees C to 100 degrees C.
Flame, the sun. A flame, the sun.
I'm sorry?
A flame.
A plane?
Flame.
Flame? Oh.
The sun. It would.
The sun? Yeah. A flame? Yeah. Well, I have to be careful what I say. The first law of thermodynamics says that energy can neither be created nor destroyed, but here, in a sense, it's destroyed in this article from last year. Scientists managed to take pure energy and create matter. So what they did was they converted pure energy into matter. But the amount of matter is very minute and the amount of energy is quite high. So in chemistry, we're still going to just follow the first law of thermodynamics. In fact, thermodynamics has been around a long time. The laws of thermodynamics have been around, would you say after, who did atoms? The theory of atoms. What's that guy's name? Anybody remember that guy? Theory of atoms guy? No.
Dalton?
Dalton. Yeah. Dalton. Did the laws of thermodynamics come before Dalton or after Dalton? Well, maybe I should say this. Even though Dalton proposed atomic theory, it wasn't widely accepted until later. Like initially, when Dalton proposed atomic theory, just the chemists were convinced. You know, it took a little bit more time for the physicists to come around to accept atoms. Eventually, both the chemists and the physicists accepted the evidence for the existence of atoms. But prior to that, you know, when atoms weren't widely accepted, did we have the laws of thermodynamics? Or did the laws of thermodynamics come after the widespread acceptance of atoms? And the answer is, the laws of thermodynamics have been around well before atoms. And ever since they've been around, people have been trying to disprove them. These mass changes are so minute, you know, you can't even measure them on even the most expensive balances. You could measure them using a mass spectrometer, but in a laboratory balance, you aren't going to measure it. So for us, we're just going to say it's conserved. Energy's conserved. And so we need 15.6 kilojoules worth of energy to increase the total energy of the water up to here. I don't know what this value is, I don't know what this value is, but I do know this value, how much we have to heat it or warm it up by. This is endothermic. That's it. So where are we going to get it? We're going to get it from, the flame is a great place to get it. If you want to heat up water, you can just throw it on a stove, you know, gas stove or Bunsen burner. You can do that. So that's a great place. So if this one absorbs energy, then somebody else loses energy. And so let's take a look at that somebody else. Except we have to look at it differently. When we divide things up in the universe. We usually look at the universe as consisting of this. A system and surroundings. We have two types of systems that we usually look at. The types of systems that we usually look at are systems that are objects, or systems that are reactions or processes. The surroundings is typically the rest of the universe. The rest of the universe consists of the same things, objects or reactions and processes. The surroundings can get a bit more complex because the surroundings are usually taken as the rest of the universe. So there's a difference here. When we have an object, like water, liquid water, the only thing that the liquid water can do is warm up or cool down. And so we can take our object and warm it up, or we can take our object and cool it down. If we change the object, for example, if we go from H2O liquid to H2O gas, that's a process. so that's a little bit different. Actually, it should be 15,700, sorry. I got the round out wrong. 15.7. So we're going to simplify our surroundings in this case. So our system's going up in energy. That energy has to come from someplace. That energy is going to come from the surroundings. So I need the surroundings to give 15.7 kilojoules of energy to the system. And the way I'm going to do that is I'm going to burn some gas. When I burn some gas, or actually there's another way of doing that. You know, my surroundings can be an object. So what I could do is I could just take hot gas. If I have hot gas here, so I'll just warm up my methane. I have hot gas, and the hot gas can transfer heat to my liquid water. And so should I just make this gas really hot? Really hot, and then mix them together. And so the hot gas is going to cool down, and the cold water is going to warm up. And are they going to meet in the middle? Actually, they won't meet in the middle. And so if I take some hot gas, let's say, what would the middle here be? So at 175 degrees C. So I'll take some hot gas at 175 degrees C, and I have cold water at 25 degrees C. And so I mix them together. And so does the hot gas cool down by 75 degrees C, and the cold water warm up by 75 degrees C? Are they going to meet in the middle? They aren't going to meet in the middle because the heat capacities are different. And so that's one way. I can just take two objects, but in this way it's going to be different. Because what I'm going to do is I'm going to burn the methane. So when I burn the methane, I start off with methane and oxygen from air. So this was there was a problem with this one on the test. Maybe you caught it, maybe you didn't. So should I have hot methane or cold methane? It's going to make a difference in kinetic energy. So what should I do? Should I take the gas out of the line here and warm it up, or should I just use it as is? What do you want to do? Should I warm up this gas, and should I warm up the air in this room? No. In fact, I don't even want to do it. The less work I have to do, the better. And so you know what I'm going to do? Should I cool it down to 0 degrees C? No. In other words, should I take my methane gas, cool it down to 0 degrees C, and then the air in this room, I should cool it down to 0 degrees C? Should I do that, or is that even more work? You want to do that? No. I don't want to warm it up. I don't want to cool it down. Although you might think, well, shouldn't we cool this down to STP? What was STP? STP is standard temperature and pressure. Standard temperature is equal to 0 degrees C. So shouldn't I be doing this under STP conditions? 0 degrees C and pressure 1 bar. Yes? No. Yeah, we'd like to do the least amount of work possible. The least amount of work possible is to leave this at RT and 1 atmosphere. Don't you think that would be the easiest? Just normal ambient conditions, 1 atmosphere, room temperature. But the problem is what happens when I ignite this? When I ignite my methane, the temperature goes way up in the flame. And then what do I form? I'm going to form CO2 gas and water. 2H2O. Now, do you know how hot a methane flame gets? I don't believe this. They're saying a methane flame gets 900 to 1500 degrees C. I don't think so. I think it's closer to 900 than 1500. They're saying a Bunsen burner gets 900 to 1600. Pretty tough. Butane flame is awfully cold, only 300 degrees C. I can't believe it. A cool flame in low gravity. So I'm not sure about the accuracy of these numbers, but it's going to get extremely hot, close to 900 degrees C. So the CO2 and water are going to be very hot. Those are products. Should I leave that at 900, or what should I do?
Get the average.
Take the average? I'll tell you what we're going to do. What we're going to do is we're going to start this at room temperature, and we're going to end this at room temperature. So it might be super hot, but I'm just going to wait. I'm going to wait and wait. And as I wait, that hot gas is going to do what? It's going to cool down. As that hot gas cools down, it's going to release more heat. And that heat we want to capture to warm up our water. Right? Do you want to waste all that heat? No, we want to capture that heat to warm this up. And so what we're going to do is we're going to, even though this gets extremely hot, we're going to cool it down to room temperature. And this is still going to be under the same conditions, 1 atmosphere. And so at room temperature, what state is water? Is that a liquid or gas at room temperature? It's a liquid, yeah. The state matters because if this were steam, have you ever gotten a steam burn? Steam burns are severe because they release a lot of energy. And so remember, in order to vaporize all this water, we're going to break all those hydrogen bonds. That costs us energy. But when the water condenses back into a liquid, it releases all that energy. And it'll release it into your skin, causing severe burns. And so the state matters in thermodynamics. We've got to make sure this is gas, 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 liquid. Yeah. So what we need is 15.7 kilojoules. And so I need to know what the initial. Well, one thing is this. These have different energies. Why did I write methane and O2 up here and CO2 and water here? The reason I wrote it is because I know methane and O2 are going to be higher energy. CO2 and water are going to be lower energy. And so the internal energy of the methane and two O2s is going to equal the initial potential energy plus the initial kinetic energy. And then CO2 and water, I'm saying, have lower energy, so that would be U final. This is going to be the potential energy, final, plus the kinetic energy, final. And then what I'm interested in is I'm interested in the change in total energy, delta U. The change in total energy is going to equal the change in potential energy plus the change in kinetic energy. The change in kinetic energy we should take a look at that here. Did the temperature change? So we started at 298 Kelvin, we end at 298 Kelvin. Did the temperature change? No. So the change in kinetic energy is 0. That means this change is entirely potential energy. And so CO2 and water we have experience with. I mean, people buy machines to make this stuff at home. You know, CO2 water. I know somebody who got one who said I should get one too, but I haven't. Because they like to drink sparkling water. But does anybody like to fill this room up with methane? You know, I'm going to buy a machine to fill this room up with methane? Well, actually, you don't need a machine. You just open the valve. We'll fill up the room with methane. Are you going to feel very comfortable? You aren't going to be feeling very comfortable because there's a potential for an explosion or a bad fire. You know, all we need is a spark. And so that reminds me of something else I'll talk about in a minute, but do you see that this has higher potential energy than this? Now, how can we measure that? Well, or how can we calculate it? Well, when we're looking at differences, like delta U here, well, what's the difference between this and this and this and this? Well, this is higher energy. This is lower energy. This is more reactive, less stable. This is less reactive, more stable. And so we have a change in potential energy here, and there was no change in kinetic energy. So this is exactly how we like to do it. How we like to do it is when we have an object, we need to make sure that the potential energy does not change. In other words, we stay the same. So this is H2O liquid, this is H2O liquid. Well, H2O liquid and H2O liquid have the same potential energy. But in this case, the temperature is different, so they'll have different kinetic energy. And so any change in total energy or internal energy is just a change in kinetic energy here. This is for an object. In other words, what we say is objects cool down, objects warm up. That's it. That's the only thing that will happen to objects is they'll cool down or warm up. Do we see any cooling down and warming up of this? No. What we have here is we have a reaction or process. In a reaction or process, what we do is we want the kinetic energy not to change. And so the change in total energy will be all due to the change in potential energy. The potential energy of a mixture of methane and oxygen is potentially explosive, whereas CO2 and water isn't. So I don't worry about a glass of sparkling water blowing up. I would worry about a container of methane and oxygen blowing up. And so there's a difference. One way we can see the difference is well, if something's less stable, that means its bonds must be weaker. And so one way we can estimate the change in potential energy is to figure out, the bonds, how strong are the carbon-hydrogen bonds? We have 4 moles of those. And then we have 2 moles of oxygen-oxygen double bonds. And we can compare that to 2 moles of carbon-oxygen double bonds and 4 moles of hydrogen-oxygen single bonds. And so we can figure out the differences in bond energies. These are more stable, therefore the bonds are stronger overall. These are less stable, and it's going to have weaker bonds overall. And so we can estimate what our delta U is for this. There are other ways of doing this as well, which we'll talk about. The other ways of doing this are via calorimetry. There are 2 types of calorimetry that we can do. So this delta PE here, the change in potential energy is, we're not going to do U final minus U initial. But the change in potential energy can be calculated using different means or measured using calorimetry. Calorimetry is a measure of temperature changes, but there are no temperature changes here. Well, we'll talk about calorimetry. Even though there are no temperature changes here, the temperature change is going to happen where this energy goes. Where does energy go? Over here. And over here, the object, water, is going to warm up. And how much this warms up depends on how much total energy change was over here. And so by this way, we can measure the change in potential energy here by having the water absorb all that energy. We could also use calorimetry over here. Calorimetry is a measure of these temperature changes. And so by monitoring the temperature changes, then we can figure out how much energy is associated with this kinetic energy change here. This is all calorimetry. So, there's one other relationship that we need here. And that is delta U is equal to Q plus W. This is called the first law of thermodynamics. Energy is neither created nor destroyed. So if the system loses energy, the surroundings must gain that energy. Or if the surroundings lose energy, the system must gain it. When the system or the surroundings gain or lose energy, they can lose it in the form of what we call heat, or they can lose it in the form of work, or both, heat and work. So, if I have this methane combusting here, I want to transfer all this delta U as heat. So we have this equation. We want to heat up the object. Q is equal to the amount. I'm going to call it amount rather than mass. Over here I called it mass. MC delta T. I call it mass because we're using specific heat. But in general, we don't have to use a specific heat. We could use the molar heat capacity or the heat capacity of an object. And so if we have one object, I put it here. If I have a mole, I put it here. So this is going to be times the heat capacity times delta T. So the amount times C times delta T. And so ideally what I want is all this change in internal energy to go over here and be absorbed as heat, which is going to result in a temperature change for the water. That's what I want to happen. But sometimes that doesn't happen. Sometimes, let's say this explodes. If this explodes and causes damage, let's say it ends up breaking some furniture, maybe breaking some bones. In order to break things, is that heat or is that work? That's work. So if I break the leg of a table, that's work. That's considered work. And that means if I do that, am I going to have as much heat go over to warm up my water? No, I'm going to have less heat. And so I don't want any explosion, because not only does explosion do work in the form of damaging property, it also does work in terms of sound. You'd hear that explosion. To make sound, that's going to cost you energy. So if you hear the explosion, well, you just lost some energy. Here, we're not going to have as much energy to heat up our water because we're doing more work. Not only that, if you see light, like a flash of light, is that heat or is that work? Well, it turns out generating light is actually work. And so the more work we do, the less heat we get. This is the first law of thermodynamics. It says that energy is conserved. And so if you're doing more work, you're going to get less heat. It depends on how you do this, how you burn the methane. So we want to be careful how we burn the methane, because in this case, we want to maximize the amount of heat. But some people, they don't want to do that. They don't want to maximize the amount of heat. They want to maximize the amount of work. Have you ever seen these CNG buses driving around the city? CNG, do you know what CNG stands for? Compressed natural gas. So they have these compressed natural gas buses. And when I see a CNG bus, I'm okay because, you know, if I follow a diesel bus in my car, I like to turn on the recirculation because I don't like to breathe the diesel fumes. Diesel fumes would be NOx, you know, oxides of nitrogen. They're all poisonous, and they all are quite irritating. But if I see a CNG bus, I don't care. You know, a CNG bus burns pretty cleanly. It doesn't form a lot of oxides of nitrogen. It's minimal. If you're driving a CNG bus, do you want to maximize the amount of heat and keep the passengers warm? Or do you want to maximize the amount of work and go farther distance? You want to maximize the amount of work. You want to kind of minimize the amount of heat because, you know, if it's a hot day, who wants to sit next to a hot engine? But due to inefficiencies, unfortunately, we can't convert it all to work. Just like when we burn it, we can't convert it all to heat necessarily because we're going to do some work, a little bit of work. Depends on how we do it. And so there's going to be a balance. And so there are different types of work that we do. Let's look at some examples. One type of work is mechanical work. Mechanical work was if there was an explosion and it destroyed the container. So it broke up the container mechanically. Another type of work would be like sound, light, generation. Or, you know, there are other types of natural gas vehicles. It doesn't have to be one with an engine that burns the natural gas like gasoline. It could be what you call a methane fuel cell vehicle. In a methane fuel cell, what we do is we use the change in potential energy there. The change in potential energy, we use that to make electricity. And so we call it electrical work. Plus whatever, you know, think of. And so if I were driving a methane fuel cell car, I want all the change in potential energy here to go into work, not heat. If I'm trying to heat up a pot of water on the stove, then I want all this change in potential energy to go into heat, not work. And so you're going to have this. We have a fixed amount of energy here because methane and oxygen is going to contain some total energy, which we call the internal energy. And CO2 and water are going to have this. And this is called a state function. That amount of energy is fixed depending on how much we have in the other conditions. And so delta U is a fixed number for a given amount. So if we burn a mole of methane, we're always going to get the same delta U. We always get the same delta U. However, we don't always get the same Q and W. And so this is like a battery. A battery always has the same amount of energy, but are you always going to get the same amount of heat and work from that battery? No, it depends on how you use it. And since we don't always get the same amount of heat and work, we call these path-dependent functions. And so we're out of time, unfortunately, but delta U, this is a state function. Q and W are not state functions. Oh, shoot. Okay, I'll stop here. Next time, I'm going to talk about constant pressure and constant volume work in calorimetry. So I'll talk about that next.